Good afternoon, everybody. This is Shaik Shafi, working as Associate Professor in the Department of ECE, B.V. Raj Institute of Technology. Today, we are going to see the extension of multiple random variables concept, that is, operations on multiple random variables. In the last class, we have seen joint distribution fxy of x comma y and joint density function small fxy of x comma y, and we have seen problems related to distribution as well as density to find the behavior of two random variables x and y. So in continuation to the joint distribution and joint density function, today we are going to explain about operations on multiple random variables. So like what we did in single random variable case, operations we have performed like expectation of x, which is nothing but mean of the random variable, expectation of x minus x bar whole square variance, and we have seen moments, there we have seen two different types of moments. One is moments about origin and moments about mean. Now we will see same operations for two random variable case, that is x and y. Now, before entering into operations on multiple random variables, I would like to give a case related to joint multiple random variables, that is statistical independence. Statistical independence of two random variables x and y. What is this statistical independence? When we can say two random variables are independent to each other, that is, if their probability distribution, joint probability x comma y and y less than or equal to y is equal to their individual probabilities, probability x less than or equal to x dot probability y less than or equal to y. And in another way, we can put it in this way. The two random variables are said to be statistically independent when their expectation, joint expectation, expected value of xy is equal to expectation of x and expectation of y. In terms of distribution, the joint distribution, if x and y are independent, then the joint distribution can be written as fx of x dot fy of y. This can be written when x and y are independent to each other. And similarly, you can put it, the definition, the two random variables are said to be independent if their joint density function is equal to individual density functions of the random variables x and y. If the random variable satisfies this condition, we can say that the two random variables are independent to each other. Now we will move on to the operations performed on two random variables. Two random variables, that is x and y. You can consider, here I am considering the random variables capital X and capital Y. In examination, you may be asked with different random variable. Notation will be changed, but the concept remains same. Now we will move on to operations. The first one is expectation of xy. If x and y are continuous random variables. If x and y are continuous random variables, how to proceed with the formula expectation of xy? Similarly, it is same as that of single random variable. In single random variable, mean of the random variable x is written as integral minus infinity to infinity. We have seen already whatever is there, that x with the density function of x dx. Similarly, for two random variables, expectation of xy can be written as two integrals. One is for x and another one for y random variable. Minus infinity to infinity, as x and y are, I am considering here, are continuous random variables. Then xy and the joint density function dx dy. So in order to find mean of the two random variables, one should know the joint density function. So if anyone asks mean of the two random variables, definitely you will be given the joint density function. Now, we will see some of the properties related to joint operations on multiple random variables. That is with respect to expectation. Suppose you have got expectation of x plus y. Then you can here you can write it as expectation of x, first property, expectation of y. So proof you can do with respect to similar to that of single random variable. Here we will see one, I will show here, expectation of x plus y. If x and y are continuous, then as we have seen the formula, based on the formula, it can be written as minus infinity to infinity, minus infinity to infinity. Whatever is there inside the expectation, you bring inside the integral x plus y and the joint density function fxy of x comma y dx dy. Similar to this one formula, expectation of xy, here applied the same for x plus y and the joint density function. Now, further if you proceed, we need to prove this one. I have considered LHS part and I need to prove this RHS. So, expand this one. Integral minus infinity to infinity, integral minus infinity to infinity, x fxy of x comma y dx dy plus y fxy of x comma y dx dy. I am separating this x to this one and the y to this one. Now write it separately. Integral minus infinity to infinity and integral minus infinity to infinity x fxy of x comma y dx dy and plus y integral y fxy of x comma y dx dy. Now, take this x separately, integral minus infinity to infinity fxy of x comma y as separately with dy and dx. Just rearrange the terms. Integral minus infinity to infinity. Similarly for y also rearrange the terms. Integral minus infinity to infinity fxy of x comma y dx dy. Next, this part here, this part is marginal density function. This is nothing but, if you remember, marginal density function, fx of x, and this one for marginal density function, fy of y. Replace this term with this one and this term as fx of x, which is nothing but marginal density function. Now you can write it as integral minus infinity to infinity x fx of x dx plus y fy of y dy. Now this is like expectation of x and formula for expectation of y. So this is the first property of under operations of multiple random variable, that is expectation of x plus y can be written as expectation of x as plus expectation of y. Similarly, if x and y are independent, if suppose x and y are given independent, there is no change in the formula, that you can write it as expectation of x plus y is it expectation of y. Then similarly, if x and y are independent, then expectation of x, y, you can perform this proof based on the knowledge acquired in case of expectation of operations on multiple on single random variable, how we have performed. Based on that, we can obtain. And here expectation of x plus xy can be written as expectation of x, expectation of y. When these two are not independent, you are not allowed to write separately expectation of x and expectation of y. So these are the basic fundamental properties related to operations on random variable, that too mean of multiple random variables. So different properties. Now these two cases are applicable when x and y are independent, continuous or discrete. The formulas are same, whether x and y are continuous or discrete. The formula, the properties are same, one and the same. So if x and y are discrete, then you have to use summation in case of integration. Replacing integration, you have to use summation. Now based on this one, before entering into the problems, we will go with moments. Here also there are two types of moments. One is moments about origin and another is moments about mean. So here moments are joint moments about origin and joint moments about mean. So as you are using two random variables, you have to name it as joint. Now, first we will see moments about origin. The generalized formula m and k equal to, if x and I am considering here x and y are continuous random variables, then m and k can be written as expectation of x power n y power k, which is equal to integral minus infinity to infinity x power n y power k, the joint density function fxy of x comma y dx dy. If n is equal to 0 and k equal to 1, this is what we call n plus k is equal to 1 is known as first order joint moment about origin. mathematically m01 equal to expectation of x power 0 and y power 1, which is equal to integral minus infinity to infinity, integral minus infinity to infinity, x power 0, y power 1, whatever is there, you bring inside the integral, then fxy of x comma y dx dy. Now it can be written as, now x power 0 means 1 and it is nothing but expectation of y, and as it is you will have to write. This is what we call first order joint moment about origin. Now similarly, m10 is also called first order joint moment, and m20 is called second order x power 2 joint moment about origin, and another second order is m02, which is expected value of y square, and another second order is nothing but expectation of xy, which is nothing but m11. So there are two second order joint moments, three second order joint moments totally, m11, m20, m02. So when you add n and k, if you get the number, based on the number, you can consider it as the order of joint moment. So here we are getting n plus 2 is n plus k is equal to 2, and here also n plus k equal to 2. So you name it as second order joint moments about origin. And here first order joint moments m01 and m10. So in this case we have got a special, m11 is a special case which is represented as expectation of xy, and which is what we call correlation rxy. M11 is considered as a special case that is represented separately as rxy, which is what we call correlation. If x and, there are again two cases. If x and y are independent, then rxy is considered as expectation of x and expectation of y. So this is written y because x and y are independent, and for that purpose, instead of directly entering into operations on multiple random variable, I have given statistical independence concept, basic concept. So which is useful here. If x and y are independent, then the covariance is equal to correlation. Correlation is written as expectation of x and expectation of y. This is the special case in case of second order joint moments about origin. Rxy is equal to expectation of x and expectation of y. If x and y are independent, then correlation is x and y are can be called as uncorrelated, which are uncorrelated. Then another case, rxy. If x and y are orthogonal to each other, then rxy is equal to 0. So which are orthogonal means there is no relation between which are independent to each other actually. X moving in one direction and x is moving in one direction and y is moving in another direction. So that means the relation between these two is nothing but, how they are separated with 90 degrees, and there is no relation between x as well as y, x and y. So because of this one, if x and y are orthogonal to each other, then there will not be any relation exists between the two random variables. That is what we call orthogonality. So if x and y are orthogonal to each other, then the second order joint moment about origin is equal to 0. There will not be any relation existing between those two. So this is another special case. Now we will move on to the second thing. We have seen origin. Now we will move on to mean. The second order are joint moments about mean. It can be written as this we have already seen moments about origin and moments about mean in case of single random variable. In case of two random variables, the moments about mean can be written as expected value of x minus x bar and y minus y bar. This is also, it is similar to m n k, where n and k, sum of n plus k gives the order of the moments about mean here. So here this is written as m x minus x bar power n and y minus y bar power k. So for second order or first order, if you consider first order m01 and m10 moments, now this is nowhere termed as m. It is termed as mu. Why? Because it is moments about, to differentiate moments about origin to moments about mean, the notation is now changed to mu nk. This is what we call technically central moments, mu 01 and mu 10. Central moments. This is first order central moment. These two are first order central. First order means n plus k is equal to 1. 0 plus 1 is equal to 1 and 1 plus 0 is equal to also 1, which is what we call joint central moment about mean, which is technically called as, separately another name is central moments. This is first order central moment, and it can be represented as mu 01 is equal to expectation of x minus x bar power 0 and y minus y bar power 1. Finally, it is written as expectation of y minus y bar. And similarly, mu 10, where you will be having expectation of x minus x bar power 1, y minus y bar power equal to, that power is 0. So finally, expectation of x minus x bar will be available in case of mu 10. These two are called again joint central moments, and that too first order joint central moments about mean. If you are saying central moments, means no need to consider again moments about mean. You can simply say it as central moment. That is more than sufficient. Now, second order central moments, mu 20, mu 02, mu 11. All these considered as second order. Why? Because the suffix n plus k gives the order which is equal to 2 here in this case. So in this case also n plus k equal to 2, here also n plus k equal to 2. All these are called second order joint central moments. Second order joint central moments. Like in case of core moments about origin, there we have seen special case, that is M11, where we have represented this as RXY correlation. Here also there is a special case in second order joint central moments. Mu11 is called as covariance CXY. Covariance. CXY can be now represented as expectation of x minus x bar and y minus y bar. This is the special case in case of joint central moments. So covariance is one of the parameter where you can find establish the relation between the two random variables x and y. And similarly, joint moments about origin, we have special case second order, that is joint moments about origin with correlation, which also used to extract the behavior of x and y, two random variables. Now, we will see one problem related to joint operations on two random variables, such as, so first one, you have two random variables x and y, and these two random variables are related with y is equal to minus 4x plus 20. The mean and variance of x are given. Mean and variance of x, that is expected value of x and expected value of x minus x bar whole square, which is nothing but sigma x square, and here it is mean, are given as 4 and 2 respectively. Then what is asking? Find correlation. Find correlation between x and y. So then we have seen correlation Rxy is equal to expectation of xy, which is a special case in case of joint moments about origin. So now it can be written as expectation of xy based on the given data. You can write x, keep it like that, and y, you replace this one in case of y, and which is minus 4x plus 20. We need to find, our aim is to find the correlation Rxy. So now you can extend this as expectation of minus 4x square plus 20x. And based on using the formula properties of expectation, minus 4 expectation of x square, as 4 is constant, you can take out of the expectation, and 20 is constant, and you can take out and you can write it as 20 expectation of x. Now this is known, given as what? Mean is equal to 4. But we don't know expectation of x square, which is also called as m2. So this is unknown. You need to find m2 first. How to find m2? We have formula sigma x square variance is equal to m2 minus m1 square. So now substitute sigma x square is known, m2 is not known, m1 is known. Now substitute sigma x square and m1 and try to get m2, such that m2 is equal to, what is sigma x square? Sigma x square is 2 plus, what is the mean here? 4. 4 power square, which is equal to 2 power plus 16, which is equal to 18. Now substitute this 18 in Rxy, which is equal to minus 4 into 18 plus 20 into 4. Now on solving, you will get this as 8. Expectation of xy, which is equal to Rxy. So like this, you can find expectation, correlation is between the two random variables x and y, which is equal to 8. So to this question, we will add one more here, that check the random variables are independent or not. Check the random variables are independent or not. How to check? We need to prove expectation of xy is equal to expectation of x and expectation of y. If this condition is satisfied, we can say that the two random variables are independent to each other. Now see, expectation of xy is how much? 8. Expectation of x is already given, that is what? 4. Now what is expectation of y? How to find expectation of y? We have already seen 4x plus 20. Expectation of y equal to minus 4 expectation of x plus 20. So here minus 4 and expectation of x is what? 4 plus 20, which is equal to expectation of y is what? How much? 4. Now substitute this 4 here, which is 4. So here 4.4, that means 8 is not equal to 16. So that means x and y are uncorrelated. Uncorrelated. And you can say x and y are independent to each other. So like this you can perform, you can solve with different problems using expectations. One more problem for today's class. Suppose you will be given random variables x and y having joint density function fxy of x comma y is equal to x plus y whole square by 40, and it is valid for minus 1 x less than or equal to 1 and minus 3 less than y less than 3. And question is, find all third order moments. So when anyone is asking third order moments, that means moments about origin only. If moments about mean means specifically it will be mentioned, or can be directly you will be asked as third central moment, third joint central moments between two random variables x and y. So third order moments means M30, M03, M12, M21. So all these things you have to find. M30, which is expectation of x cube and y power 0, and here expectation of x power 0 and y power 3, and here expectation of x power 1 and y power 2, and here expectation of x power 2 and y power 1. We need to find these things, values for this. So I will explain M30, so that based on that you can try these from your side and try to find what are the remaining three third order moments about origin. So now first we will consider M30. M30 is one of the third order moment, that is 3 plus 0 is equal to n plus k. The order is giving as 3, obtaining as 3. Now M30, it can be written as expectation of x power 3 and y power 0, that is no need to write. Now as per the formula of joint density function, you need to write two integrals, one is x and one is y. Even though y term is not there, you have to write, because you have got the joint density function, minus infinity to infinity and minus infinity. X power 3, the joint density function x comma y dx dy. So the limits are given as, for x limits are minus 1 to 1, minus 3 to 3. So this is generalized formula. So but as per the formula given, the limits are changed from minus 1 to, so you can consider this as this integral for y, that is 3, and here it is 3, and here for x minus 1 to 1, you can consider anything. X power 3, what is fx of joint density function fxy of x comma y? X plus y whole square by 40 dx dy. Now separate these 1 by 40 integral minus 3 to 3 integral minus 1 to 1 x power 3 x square plus y square plus expand it 2xy and dx dy. Now separate the x terms and y terms. 1 by 40 integral minus 3 to 3 x power 5 plus integral, here you are missing minus 1 to 1, and x power 5 plus x power 3, you can write small letters here, and y square plus 2, here also small, x power 3 and x power 3 and x power 3. 2xy x power 4 into y dx dy. Now we will do with integration with respect to x first, then we will continue the same with integration with respect to y. So when you do with respect to x, integral, outside integral is for y, so this becomes x power 6 by 6 plus x power 4 by 4 y square plus 2 x power 5 by 5 and y over the limits minus 1 to 1 dx, sorry, only dy. We have done with respect to x the integration. Now 1 by 40, and now substitute upper and lower limits here. You will be getting here, when you substitute upper limit, 1 by 6 plus 1 by 4 y square plus 2 by 5 y minus, and substitute the lower limit, 1 by 6 plus 1 by 4 y power 2 minus 2 by 5. Here y is there, y you write down, y, and dy. And now on solving, you will be getting minus 3 to 3, 1 by 6 plus 1 by 6 minus 1 by 6 goes, and 1 by 4 y square and minus 1 by y square, and left over with 2 by 5 plus 2 by 5 into y dy. Now it can be written as 2 by 5 and 2 by 5, 1 by 40 minus 3 to 3, 4 by 5 y dy, and take it out, 4 by 5 into 40 integral minus 3 to 3 y dy. And this can be written as 1 by 50 integration of this one y square by 2 over minus 3 to 3. And now on substitution, the limits, this is 9, 3, when you substitute 9, it will be 9 by 2 and minus 9 by 2, which is equal to 0. So the one of the third central moment, M30, what we got, equal to 0. So I request you to check M03, M12 and M21. You will get all third order central moment here also equal to 0. You please try from your end, so that you will get practice how to solve, how to get the third order central joint moments about origin. So this is what all about operations on multiple random variables. Today we have seen statistical independence concept, then we have moved on to operations on multiple random variables. We have considered x and y are continuous random variables, then moved on to the expectation concept for two random variables, and we have seen moments about origin and two problems related to moments about origin, that is nothing but joint moments about origin. In the next class, we will extend this topic, extension of this topic with respect to x and y discrete random variables, and few more problems related to both continuous and discrete we will perform. Then we will move on to joint central moments, that is mu11 or mu nk. The concept of joint central moments we will see, and we'll wind up the operations on multiple random variables in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.